Okay. Yeah, thank you very much for this invitation to this colloquium, and thank you, Benoit, for the introduction. So I ask, people what would be of interest, and so I want to talk about some work we did over the last few years with Lisa Hartung, who is in Mainz. She used to be a student of mine, but now she is a colleague, and that was about the use of Feynman-Kac representations for basically FKPP equations. And so this is, okay, so I will tell you this story. And let me just start with an overview. So there will be three parts. One is classical, just a brief review and just of the heuristic part of the proofs of Bremsen's analysis of the FKPP equation, which is what originally motivated us because we were working on branching Brownian motion and sort of a classical FKPP equation. I mean, that is the main tool that was used by Bremsen. You can say, I mean, it's something Bremsen analyzed the FKPP equation, and that can be by duality give you results about branching Brownian motion. So I will just show how he used Feynman-Kac to analyze this equation. And when we looked for extensions to systems for various reasons, okay, systems of FKPP equation, of course, are very natural from the point of view of biology, and they have been analyzed a lot in the analysis literature, so there's a lot of stuff. And we thought maybe one can also do something with Feynman-Kac there. So we came to a particular case which we call reducible systems, and I will explain this, a particular paper that we found interesting. And when in the last part of the talk, I will speak about work in progress where we have not really complete results on okay, so I will tell you this later. So there will be three parts. Now, 1947, basically, Feynman and Kac, not quite independently, but actually sort of being together and working, they got this classical result, which you learn in the first course in whatever, at least certainly if I teach stochastic analysis, and this will always be done, which is you have a linear parabolic PDE in one component. This can be in any dimension. I mean, the X can be any dimension, and then so you have this diffusive term, and you have which I would call a potential term. So it's U times some function K, and then under mild conditions, some growth conditions on K, you can get that representation for the solution in terms of an expectation over a Brownian motion with this funny, and this you will keep this funny exponential to the integral of this potential. Right? So this is sort of like a source term, right? And so this is classical, and it's quite useful. I mean, it can be used to prove existence, and you prove their properties and so on. But so this is for the linear case. Now, the equations that Bremsen and many people, starting with Kolmogorov, Petrovsky, and Kotlus and Fischer, coming from either the spread of an allele an advantageous allele in a population in one dimension, or you can also think of it as a population dynamics equation where you have a spread of a population in on a one-dimensional area. This is this nonlinear PDE, so it looks exactly like the linear one, except that here you have a nonlinear term, in general a function of UTX, and for the purposes of this talk, just think of this U f of U to be one U times 1 minus U. So when the U is, let's say, a growth term, and the U squared minus U squared term is a competition term, so think in terms of population dynamics. And when you so you get this, and when the interest in this is, you think of initial conditions to be just Heaviside conditions. So you say you have a population which is in equilibrium. So one is one equilibrium up to at time 0 on the half plane, and then you ask what happens, and that's the classical result that you get this convergence to Trevelyan-Wake equation. Now what Bremsen did was to say, well, we would like to use this Feynman-Kac representation. And how do you do it? Well, you say, well, you just say this f here, you can always write, well, you can write f as f divided by u times u, right? And so then you can write this term here, right, as k times u, where k is now f of u divided by u, right? And think of f of u divided by u. In this case here, it's just 1 minus u. So of course now this k is itself a function and depends on the solution, right? And if you write the Feynman-Kac's representation, you get now, instead of a representation which gives you a solution, you just get an integral equation from this partial differential equation, right? So you have u here, and also the u sits also here in the k, but we have a representation, and it might be useful, and Bremsen found out that this is actually quite useful. And let me just explain you roughly what we say. So we go back. So we have u is equal to this e to the integral 1 minus u. And then you integrate over this Brownian motion that goes from x, and it has to go to the negative axis, to where the initial conditions were. Now you see e to this integral, I mean, it wants to be large if u is essentially 0, right? So if this Brownian motion here manages to be in a region all the time where the u is equal to 0, then you get something like e to the t times the expectation of it. Right? And this you can, so to make this a bit more explicit, you can write this expression in terms of the endpoint of a Brownian motion, which is at the bt, which we call now here z. Right, so this is the z, and you integrate over the end position of this Brownian motion, and that gives you this Gaussian factor here. And then here you write that the Brownian motion bs, you write it as a linear function plus a Brownian bridge from 0 to 0. So it's basically this picture that I have here, right? So you have a Brownian motion that goes backwards in time from t to x, and then you can write as this linear thing plus the green thing, which is a Brownian bridge from 0 to 0. Right? And now the whole idea is that you use consecutive bounds to analyze, to get into this this thing. So the first thing is you say, well, I mean, you cannot do better than make this u equal to 0. Right? So the immediate bound is to say, well, just this ut of x is smaller than if you put here, I mean, all this stuff cannot be better than e to the t, so you get it smaller than e to minus x squared over 2t plus t. Right? I mean, we basically, just go back, we had this integral from minus infinity to 0, so you have this z, which could be negative, but the best thing it can do, it's like if it was equal to 0. So you have this nice expression, right? And now you see, if you look at this thing, you see basically, well, this will certainly become small if x is larger than square root of 2t. Right? If x is larger than square root of 2t, then this squared term dominates the t. And so you know that we have this a priori bound that this u of square root of 2t minus s plus the Brownian motion is roughly equal to 0. There's a bracket missing. Okay, let me just put it. If only the Brownian bridge stays above this line, so it just stays positive, right? When you have this, and so you say, well, actually, it's not so difficult for the Brownian bridge to stay positive. That costs actually something like 1 over t to the t to the 1 over t, right? And so then basically you say, well, actually, if you just make this bridge, if you look at now, I should go back to the pointer. Let's go away. No, please go away. Okay. If you look at x of the order square root of 2t, well, then basically this is roughly larger than something which is only polynomially small, right? So that corresponds to the upper bound, which says that this is roughly, it's getting small once you go a little bit beyond square root of 2t. It says, well, also at square root of 2t, you are still only polynomially small. And this is basically the idea behind this analysis of Bremsen. And what he did with that is, I mean, with some substantial extra work, it's not trivial. He says, well, this gives me the precise, this we can make precise to show that actually this U converges to a traveling wave solution precisely with a shift which is square root of 2t minus 3 over square root of 8 logarithm of t. Right? This 3 over the logarithm of t, that is just corresponding to this decay 1 over t to the 3 over 2. Right? And so this was with basically Bremsen's PhD thesis. And you know, while things are complicated in detail, the basic idea is just that you look at this representation, and then you go to you go to a place where this exponential term starts to this decreases, and basically all the way up to where you try to make this part as big as possible. Right? And that is not very costly, because it's only polynomial cost for a Brownian motion to do what it does, and it gains an exponential because if you get rid of this u, then you have an e to the t, right? And so that gives you this behavior, right, that you have. Okay, so this is very roughly the approach of Bremsen to analyze this convergence to traveling wave solutions in the FKPP equation. And now we wanted to extend this to systems of FKPP equation which describe populations or the advance of populations in space with different types. And in general, there's one problem if you have, I mean, even if you have a linear system of parabolic equations, there's basically no useful Feynman-Kac representation. I mean, this is sometimes used in quantum physics, and you write something, and then this is called a time-ordered exponential. But if you look at these things, you're basically totally useless. I mean, more or less, you can't do anything with that. So the point to write as soon as you have a system and you would like to repeat this, it's not completely obvious how to do this. So the first, I mean, so we looked, so you know, we said, well, can we find something? And then actually, Lisa looked in the literature, and we found this nice paper by Venegas, Ortiz, Allen, and Evans from Edinburgh, where we looked at a system of FKPP equations which describes two species that interact with by mutation and horizontal gene transfer. So let me just write in these equations. We have a type U and a type W. We can again have these diffusion terms like in the normal FKPP equation. You have a competition and a growth and competition, which is symmetric. So you have U, and then you get a competition with itself and with W equally strong. And for the W, it's the same. So this is just a nice thing. And then you have a term, you know, these terms gamma UW plus gamma UW. So that corresponds to an interaction between the U and the W. A particle produces, you know, a flow from the U type to the W type. Right? So if two particles, if they meet, so then you have when you get the U thing transforms into a W, and this happens at a certain fixed range gamma. And the other thing that happens is a mutation. So the W can mutate into a U with this rate beta. So that's kind of a nice system. And now the advantage of this particular system is that by accident you can somehow semi-decouple it, in the sense that if you introduce the total population, V W plus U, then you can add these two equations together, and you end up with an equation for the V, which is just the ordinary FKPP equation, right? And then you have an equation for the W, where this V enters into the competition term right here. So you have the WV term here. And so what you have right? So now basically you can solve first for the V, which we already know how to do because that is what Bremsen had been doing. And then we can feed it into the W equation, and then what you have is basically a time-dependent, explicitly time-dependent FKPP equation for the second component, right? And then you can say, well, now you can try to analyze this time-dependent equation, and then you can use this Feynman-Kac representation, right? So we call this semi-decoupled. So see the V thing, that's again, we start with heaviside initial conditions when you get, well, actually, we start here with, to make it easier, with the stationary initial conditions when the V is simply this traveling wave, moving around with the speed square root of t. And roughly speaking, you can just think of this as something which is like the step function, which moves with the speed square root of t to the right. And then we insert this into the W equation. So now you get a single time-dependent FKPP equation, and you can write as before, you can write this Feynman-Kac representation a la Bremsen. I mean, no, that's because again, if you go here, you have this W, divide this thing by W, and then what you have in the exponent is here something which has the W itself, and it has this F thing which comes from this explicitly solved V component. And then again, the idea is to use successively bounds to analyze this. And well, so what are the bounds? I mean, the first bound you can get is by saying, well, this F is between 0 and 1, so you can actually get an upper bound by putting it equal to 0. I mean, put this equal to 0. Then you have an upper bound which looks like, again, a normal, I mean, the upper one looks like a normal FKPP equation with just this extra 1 minus beta and gamma. And and in the lower bound, you put the F equal to 1, which is the worst case, and then you get the same thing, but here you get, instead of 1 minus beta, you get gamma minus beta. And from this, you can derive bounds on the, already a priori bounds on the speed of, oh, there's a rho, which should be a rho, never mind, of how this W wave advances. Right, so I have maybe you should look at this picture here. So the picture is you have the blue thing is this V, that is the total population, and that we know evolves like a traveling wave moving with a speed square root of 2. Right, so we have basically this thing goes down at square root of 2t, and that moves, goes over here. And now the W, it cannot move as fast. So what you know is that Miss W may move maybe with a certain speed rho, but that is between square root of 2 beta minus gamma and square root of 2 1 minus beta, right? And so that goes on. Now, the point is that if instead of having this traveling wave here, if a V would be just constant equal to 1 all the time, right? Then this upper bound, this lower bound would be correct. And then you would actually move with the speed square root of 2 beta minus gamma, and that would be just simply another FKPP wave which advances with that speed. And now what they found in this paper, and it's not the first ones who found that, but I mean, this is somehow a kind of general feature, is that in fact if the V wave is not completely filling space, but it's just at this position square root of 2t, then the motion, when this W wave is sped up, right? It moves at a faster speed, and the question is, what is this speed? And then our question was, can the FK representation help us to compute this speed and also to understand why this is actually happening? And I think the more interesting part in what we looked at is that this FK representation is really giving you a very nice way of seeing why you get this acceleration. You know, I just looks a little bit complicated. So we write, we take again heavy side initial conditions and we write sort of these typical approximations like, you know, of this thing. You have and you look at WTX. So you have this Gaussian term which comes from the endpoint of a Brownian motion to be at X. And then you have, so now now you have this exponential thing, and the exponential thing you have here, well, this is just the W itself, and here you have the F, right? And now if you see if this argument of the F here is an area where the F is roughly equal to 1, then we get basically this behavior like in the lower speed. So in order to get something which can advance faster, we should be in a region where the argument here of the F is larger than 0. So basically I make this picture here. If you so you see this, so this wave here advances at a speed square root of 2x. So you have this xt minus square root of 2. And then you have on top of that, you add on this Brownian motion. So this F here is roughly, I mean, so this term here is roughly 1 minus gamma below this line over time. This is basically the S thing. It goes from 0 to here. So if you're here, this thing is equal to 1 minus gamma. And if you're above this straight line, so if a Z moves in a way that you're above this line, then you pick up a 0, right? So in order what you gain, so what you and the blue thing that I plotted here, this blue, I mean the red thing, sorry, the red thing is the Brownian motion. Right? So this Brownian motion gives you a gain if it is above this line. So in the picture here, it would mean that if you are in this situation, you want the Brownian motion to explore the area where the W is 0, right? So you want to you get a 0 into this exponent, right? And so now of course, if you look at this picture, right? Normally a Brownian bridge would like to be like a square root of t, you know, above on 0. Now here it has to go up by something of order of t, right? So remember in the original Bremsen thing, the Brownian motion, I mean, this Brownian bridge had to do just, you know, a little bit what it almost wants to do with just a little handicap that it should stay positive. And now you see here, if you want to gain something substantial, it has to move to do something very unlikely, right? And so if you think about this as well, it has to, you do something very unlikely, but then if you do this, you know, over a time, which I now call tau alpha here, but you can gain something which is of the order e to the 1 minus gamma times this time that you have. And in fact, you can write this, if you define this time tau alpha, the time that you are spending above this line, and now I have rho minus square root of 2t minus s, you get an expression which is kind of nice. You get that the wt rho t, you have this e to the rho squared t, which is the Brownian, with cos to go to here. This comes from the endpoint of the Brownian motion. Then you have what you get for free, e to the t times gamma minus beta. Now that's what you just get if you don't make any excursions. And then you get the expectation of e to the 1 minus gamma times this time that you spend above this line, right, for this Brownian bridge, right? So in order to do anything, you have to compute this Laplace transform of the time, right, of this time that the Brownian bridge will spend above this such a line, right? And so this, fortunately, you can do relatively well. And so we did this, and we get e to the, so this Laplace transform is, well, it gives you nothing if here is the lambda, the parameter is too small, right? Because when when it's just too unlikely to actually pick up something here, but if two lambda is larger than alpha squared, you get a nice expression that this Laplace transform is e to the t alpha minus square root of 2 lambda squared over 2. Right? So this is a computation which takes some time, but you can do this relatively elementary. And if you plug this in, you can actually get the speed of the wave. I mean, that's a little bit of work, but what you get is that this speed of the W wave in this advancing full wave is here square root of 2 minus square root of 2 trial gamma. I mean, you can read it. And here, if beta is smaller than something, and it's actually equal to the smallest possible speed, which corresponds to the case when the V wave is already completely invading, if beta is too large. It's larger than this critical value. Right? And the nice thing is that this formula has a very nice explanation in terms of balancing the gain, the exponential gain, if this Brownian motion goes before the front of a W wave against the cost for doing this. Now, these people, as Ortiz and others, they have another formula for this speed, which we didn't understand, and which is much more complicated. It becomes the same in the limit as beta goes to 1. But the other papers by Lam Yu and Holzer-Scheel, which treat more or less a similar case for purely analytic methods, and it seems that they have compatible results on the speeds. It's always very difficult. I mean, it's sometimes difficult because of the equations that people write are slightly different and the conditions are complicated. But this seems to be the correct answer. And we have, of course, I don't say this, but we have more precise results, not only about this speed, but also of the localization of this wave and so on and so forth. So in this case, things worked out fairly well, but it benefits. I mean, it depends on the fact that one of the equations becomes autonomous, and then you can just deal with an equation. The second equation is just an equation with a time dependence, explicit time dependence in it. Okay. So when we said, okay, that's nice, but what happens if we don't have it? You see, the problem is it's this fact. Maybe just go back to this equation. The fact that you can get this reduction here to this almost decoupled system is really very, very delicate. I mean, as soon as you change anything, it's not going to work anymore. If you change the diffusion coefficients, for instance, from 1/2 to 1/2 and something else than 1/2, this is not going to work. If you put the competition things slightly different, it's not going to work. So this is somehow, unfortunately, very, very special. So you said, no, can we do something also in the case when this is no longer so special? So we decided to look at the classical equation, which also studied a lot in the literature, just a competition diffusion equation, where now we can have, I mean, it's again two equations of the FKP type. Now you have two different diffusion coefficients. We will take one larger than the other, so it's 1/2, and the other one is delta squared over 2, where delta is larger than 1. And here we can have different competitions between the different types. So you always have one for the same type of itself, and you have a different one U with V and a different one from V on U. So it's sort of asymmetric, and we will always consider the case where gamma is larger than beta, and in that case there is a stable coexistence fixed point. So if you have a constant solution when you have these two fixed points, U star and V star, which you can compute, and they're stable. Right? And this actually, so basically we used, I mean, we're basically based what we did mainly on a paper by Lin and Lee from 2012, where we gave actually rather nice, for us understandable analysis with basically PD techniques of these equations. And now, see what do we then do? I mean, say, well, you can not write, as I said, we cannot write an FK representation for this system. But what we can just simply do, we can just write two FK representations for each of the equations. And we prefer to write it like this. I mean, we said, well, we make a rescaling in space, and so have this U tilde, which is just U at t times delta and delta x. So you just shift space, and then you get, and then this had then the advantage that you get two representations with the same type of Brownian motion, just ordinary Brownian motion. And then you just have these two equations, but of course they're coupled, and also you have these integral equations which are coupled, and in this exponent there appears, in both cases, with both types. Right? And so, well, the thing is, I mean, we just to proceed a bit like in the other example, just proceed by using successively upper and lower bounds. Well, you can always bound things by putting, by knowing the worst cases for V's and U's, and then you can just produce. The hope is to get by successively using upper and lower bounds, you can get what happens. And of course, you also have this a priori bounds, which tell you a number of things. So I will mainly show you that this how this looks in the picture. So here we have a picture for the so the first thing is that this U wave in that case is the one which is faster, and you can show that this cannot basically be, well, the speed of this U waves, that will be square root of 2 delta. So you're going here, and the speed of the now the speed of the V wave will be no more than square root of 2t. That's because it has this diffusion coefficient 1/2, not delta squared over 2. So basically that you will have to be behind, even if there was no U. And also that it is not slower than square root of 2 times 1 minus gamma t, because this is what would happen if U is constant equal to 1 all the time. And here, by the way, this is 1. So maybe I just put this here. So this side here is 1. And now you can say, let's say we have the rho is the front of the advance of a V wave. Then you can show, it's not very, very difficult, that the U wave looks exactly like it here. So if we have no V in this area, then the U will go to its equilibrium up to its own front, and so it will be roughly be 1 here, and then it goes down at this time here, right? And now, so what is the idea? The idea would be to say, well, we also know that in any area where you have where V and U are positive, you go to U and V will be close to this equilibrium value. I mean, you can show that this is just the dynamical system attracts to this stable equilibrium, so we will go where they will be close to there. So the only thing is, which is kind of subtle and which we have not completely sure, is whether do we have monotonicity. If we have the largest point where the V is positive, is it true that the event will stay positive? If that is true, then it will stay near its equilibrium. The picture will look like this. And then if you do the same thing as we did in the previous paper, so we advance the way how you get a speed up here is by the V wave exploring the region before the U wave, where in this exponent you have a 0, right? So and if that is, so again, you get this upper and lower bounds, and if you can just so if you assume that the v thing is somehow monotone in that thing, then you actually you get the formula for the speed, which I will not read. But it's so again, it's for in a certain range if the delta is small enough. So basically, delta here you see that if delta is too large, then it's too costly to move in front of this wave, and so therefore you don't gain anything. So you get just the same speed as if the u was equal to 1 all the time. But if delta is smaller, you get actually a rho which is larger than this value, and you get again this acceleration, right? And there is a condition also, an upper bound on this possible speed that you will get. Now this actually is also in general a lower bound, but we don't have so we know that this will advance at least that fast, but the problem that we still are not really, it's a silly problem, is that we cannot exclude somehow that there might be somewhere a region where the v goes to 0 and when it comes up again, and then that produces a term which we cannot control. So this is something we are trying to work on. Looks rather silly, but that's just unfortunately the situation. So anyway, but anyway, again, if we can solve this problem, right, then we have a very nice explanation again for getting the speed, and a very nice way to compute this formula for the speed, which we didn't see. Maybe somebody has in the meantime obtained this, but we haven't really seen that. It was definitely not one of the things which is open in the Lin-Lee paper, but maybe someone. So just a final comment before I stop. Yeah, okay. So as I said, we show that without the sum that the v advances at least at this speed, and we would need to know some monotonicity properties in order to show that it is actually correct. I think that should be true, but we don't. So the message for me is that this Feynman-Kac representation can be used also in systems. It gives a nice intuitive explanation for these acceleration phenomena for speeds in co-evolving waves, but there's still a lot of things that are complicated. Of course, there are lots of other equations and lots of situations which are more complicated. So we hope to continue with this work, but at the moment we have been stuck for a while. Okay, so thank you for your attention. I think I'm in